Alright, well, good day and welcome to my shop. So today on the bench we've got an old CNC lathe that we're going to be retrofitting to run on one of these cheap and cheerful Arduino based GRBL controllers. I picked this lathe up a few years back and it had sat unused and unloved in the corner of its previous owner's shop for some time, and I got it with grand plans of getting it up and running, but instead it mostly just sat unused and unloved in the corner of my shop. So I think it's about time that we get things up and running. The machine's an old spectralight machine, which under the skin is really just a CNC-ified Sherline. I'm sure in its day it was reasonably capable, but to get it up and running in its current state would have required me to dig up an old computer with a parallel port and get some unobtainable software that probably only ran on Windows XP, and it's a whole can of worms that I didn't particularly feel like opening up. The other sticking point is the ability to do threading. Now, this might be a little contentious, but I'm kind of the opinion that a lathe that can't cut threads isn't particularly useful. Sure, there's stuff you can do without threading, but for most of the things I'd be interested in doing, it's kind of a must-have. Now, to do the threading, the machine needs to be able to control the position of the table, or the saddle, relative to the rotary position of the spindle. Your standard manual lathe does this with a gear train that makes a mechanical connection between the rotary motion of the spindle and the translational motion of the saddle. Now, CNC machines take care of this by tracking the position of the spindle and calculating where the carriage ought to be on the controller. I'm going to accomplish this using a Hall effect sensor, this guy here, and rare earth magnets placed around the circumference in a ring on this spindle pulley. This guy can just clip on right there. The polarity of these magnets alternates south-north, south-north, and as the spindle rotates, the output from the Hall effect sensor will be pulled high or low depending on the polarity of that magnet. Now, I'm using 22 magnets, meaning that each pulse is a 22nd of a rotation, or about 16 degrees. And this gives good resolution. However, if we want the thread to start consistently at the same place every time, we also need to track the absolute position of this spindle. So we need to know where 0 degrees or 12 o'clock is. To do that, we're going to accomplish this by flipping one of the magnets. So we'll have south-north, 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 north, north, north. So we're going to have a double width pulse that happens once each rotation, and we can use the trailing edge of this pulse to identify 0 degrees. And this will give us our index for the threading. Now, one of the problems with GRBL is that it makes full use of the capabilities of an Arduino. That means there's no real processing power left over for any other features. And the problem is that Arduino doesn't have any processing power available to keep up with the high resolution encoder. So my solution to this is to offload the spindle control to a different microcontroller. I'm going to be using one of these teensy 3.2s, which has plenty of computational horsepower to keep track of the spindle position, and then some. So as an added benefit, I can also implement proper control to maintain a very consistent spindle speed. The way all this will work is that the teensy is going to take a spindle speed request from the Arduino. The teensy is then going to start the motor drive, which at this point is about the only original piece of control hardware left. The teensy is going to keep the spindle running at the correct speed by monitoring the spindle encoder, and then once per rotation, it's going to output a pulse back to the Arduino to let them know the spindle is at 12 o'clock. This provides the benefit of a 22 pulse per rotation spindle speed encoder, while also only requiring that the Arduino keeps track of 1 pulse per rotation. First things first, we need some stepper motors to drive our linear motion. I'm using these NEMA 23 dual shaft stepper motors, and I've 3D printed some strain relief grommets, I guess you could call them, to route the wires and keep everything nice and neat. The wires coming out of the motor, you don't want any mechanical stress on them to prevent them from breaking, so this takes care of that. So let's take a look at how these go together. Next up is cable termination. Now I'm using these cheapy 4-pin GX16 aircraft connectors. According to the specs, the terminals in these are rated for 5 amps, which personally I think is pretty optimistic, but they should never really see that much current, at least not in this application. Another thing I'm doing here is I'm using the metal shell of this connector to shield the connector. I'm wrapping the drain wire around the outer jacket of the cable and then clamping it with the strain relief on the back of this connector. All of these connectors connect into this I/O shield on the main box, and this plate acts as a star grounding point for all of the grounds. This gives a nice grounding strategy which should be good for avoiding ground loops. I'm a little unsure how this is going to work out long term, given that this is kind of a little bit of a dirty hack, but time will tell how well this holds up. This rat's nest is the spindle controller board. The teensy that does the heavy lifting is in the middle, with a logic level shifter here for communication with the Arduino, and then a bunch of opto-isolators over here to provide some isolation for the more delicate internal electronics like the teensy and Arduino. I'm not going to go into a whole lot of detail because we could end up pretty deep in the weeds with this, but if you have any questions or want to see more about this, let me know in the comments down below. Now all that's left is to put things together. Here I'm using pretty reasonably priced components. I'm using TB6560 stepper motor drivers with an Arduino Uno and this Adafruit wing shield. The teensy daughter board here and a separate power supply which provides power to the dirty side of the opto-isolators all get mounted onto this 3D printed tray to keep everything nice and neat. This also helps with cable routing and management because the cables can be screwed right down to the board using little 3D printed clips. With that, let's get things assembled. Shop's a total mess, which is a good sign that something happened. Now we've got all of our different components nicely terminated and ready to go into the machine. We've got our control box, complete with our controller, nice and neatly laid out. We've got our nice front panel connection for USB control over the controller, and nice pluggable ports on the back for each one of the different components that are going to run this lathe. If this was something you enjoyed, please consider subscribing. Up next is going to be the complete assembly and hopefully some test cuts on this bad boy. If you had any questions or comments, drop them down below. I'll do my best to get back to you.